In this chapter, we're going to be discussing nuclear chemistry. Isotopes of atoms can be stable or unstable, and the stability of the isotopes is based on the number of protons and neutrons in the atom's nucleus. If you start stuffing too many protons and neutrons in a nucleus, it becomes unstable. And unstable isotopes spontaneously decay, and when they do so, they emit what we know as radiation. So radioactivity is the spontaneous disintegration of the nucleus of an atom with the emission of particles and/or radiant energy. When they emit these particles and they lose protons and neutrons from their nucleus, the atom changes into something different, and that process is called transmutation. Transmutation is when one element is changed into another because of changes in the nucleus. So the particles that they give off are also called emanations, and there's different kinds of emanations depending on the type of isotope that's decaying. And these can all be found in Table O. So this is Table O, and it's a chart of the different kinds of emanations that are used or that are in radioactive decays. So this column of the chart here has their names. This column in the middle has their notation, what they would look like in a nuclear equation. And this column here has their symbols. So the first one we're going to look at is alpha decay. So alpha decay is when an alpha particle, and an alpha particle is written like this. An alpha particle is the nucleus of a helium atom. So it's a helium atom without any electrons. It's basically coming out of the nucleus. And alpha decay is when one of these particles is given off as a result of nuclear disintegration. So here's an example of what an alpha decay reaction would look like. So here we have radium-226. So this is a radioactive isotope. Whenever you're naming an isotope, you name the name of the element, radium, and then you say the mass number. Remember, the mass number is the larger of the two numbers, and it's always on the top, the superscript. So this is radium-226, and you already know it's alpha decay. So it's going to give off an alpha particle. So we're going to write an alpha particle as one of the products. So it's your responsibility to find out what radium transmutates into after it loses an alpha particle. And the way we do this is we just keep an accounting of all the mass numbers and the protons. So if radium weighed 226 because it had a total of 226 either neutrons or protons when combined, if I lose 4 of them, I'm going to have how many left over, and that's what we need to decide. So you can do the math either in your head, or if you need to use a calculator, that's fine too, but 226 minus 4 is 222. Okay, at this part, we still don't know the identity of the missing element. Now, you could go to your periodic table, and you could scan, and you could look for something that weighs 222 atomic units. But it may or may not be right, because we don't know if this product is an isotope or if it's a different isotope than what's on the table. So this isn't specific enough to give us our answer. So we get our answer based on the atomic number. This is more specific. So radium had an atomic number of 88, and after it loses an alpha particle, it loses 2 protons. So if I take away 2 protons from 88, 88 minus 2, the number that I'll write here for my missing product will be 86. Now you know what the missing element is, or what the radium turns into after it transmutates. There's only one thing on the periodic table that has 86 protons, so you go and you scan for an atomic number of 86. And that, of course, is radon, Rn. So this is how you write a nuclear reaction, or predict the products of a nuclear reaction. The concept is very simple. All the mass numbers on the left need to equal the mass numbers on the right. 222 plus 4 is 226, and 86 plus 2 is 88. It's the same process for no matter what kind of emanation is given off. So our next one is beta decay. So this is when a beta particle is given off as a product of nuclear disintegration. And a beta particle, you can look on table O, looks like this. So a beta particle is an electron. So we have an electron Electrons, of course, have no mass, so it has a 0 up here, and it has a unit of negative charge, so it's going to cancel out any protons, so it has an atomic number of -1. So let's do an example. We have thorium-234, and it's going to undergo beta decay. So after it loses a beta particle, we need to be able to predict the product that it transmutates into. So the mass is really easy, 234 and 0. That means my mass has not changed. It's still going to be 234. Now the atomic number, we need to think, what must the atomic number be here so that when I add a -1 to it, I get 90. And that, of course, is 91. The only thing on the periodic table that has an atomic number of 91 is Pa, protactinium. Okay, next we have gamma radiation. Gamma radiation gives off gamma rays, and a gamma ray looks like this. It's kind of like a weird little Y, and it has no mass, and it has no atomic number either. So these are actually not particles. They don't have mass or charge. They're just energy. They're similar to high energy X-rays. And if a element undergoes gamma radiation, it just reduces the energy content of the nucleus, but it doesn't affect the charge or the mass. And the product is the same thing as the reactant, it just now has lower energy. So how do you know what type of emanation a particular isotope goes through? In our last two examples, I told you what type it was, but you need to pick out the type of emanation for the nuclear reaction questions that you may have to do on the test. So the way you know is you look at table N. So table N here has a lot of important information. What is important for this part of the notes is this third column here. Well, we have the names as well. We have the nuclide symbols. So these are all the ones that they can ask you about on the Regents. And then in the third column over, we also have the name. So we have the symbol. If they give you the name, you could look up the name and then write the symbol. But this third column here has the decay mode. So this will tell you what type of emanation each of these goes through. Now, if you don't know what these symbols mean, okay, B with a little minus, B with a little plus, a weird little A, you need to go to table O. Okay, so table O will remind you what these symbols mean. So if you have a question asking for writing the nuclear reaction for a particular type of radioactivity, and they give you, say, this little A, you need to look it up and see that the A is an alpha particle, and alpha particles look like this, and then you can just fill in the equation. Okay, so let's do an example. Write the formula for the radioactive decay of potassium-37. So here's potassium. They tell us that it's potassium-37, but they don't give us the atomic number. It's missing. And we saw from our examples that's important. We need to know that. Well, the good news is they don't need to give it to you because they told you it's potassium. So if you don't know what potassium's atomic number is, no big deal. You just go to your periodic table and you look it up. It's in group 1, and of course it has an atomic number of 19. So next we need to figure out the type of decay mode. So we go to table N and we scan until we find potassium-37. And there it is, potassium-37, or K37, undergoes this decay mode. It's got this little B with a plus sign. So we didn't do an example of that. So you need to know to go to table O and figure out what the B with the plus sign is. That's called a positron, and positrons look like this. Positron is like an electron, but instead of being negatively charged, it's positively charged. Okay, so we're going to write that symbol in, 0 with a +1. All right, now we have everything we need to find the product, what potassium-37 turns into after positron decay. So again, the mass numbers on the right need to equal the mass numbers on the left. 0 and a 37 will equal 37. And then I ask myself, what plus a +1 will get me to 19? And that's 18. And then we go to the periodic table and see who is atomic number 18, and that's argon. So we are turning potassium-37 into argon-37 through this positron decay. Okay, another thing that you're sometimes asked about is the penetrating power of these particles. So penetrating power is the ability of the radiation to pass through matter. Sometimes you're asked to rank them or figure out who's got the most or who has the least penetrating power. So gamma particles have the most, and alpha particles have the least, and beta particles are in the middle. So alpha particles don't have a lot of penetrating power. They could be stopped by a sheet of paper. A beta particle will go right through that sheet of paper, but it could be stopped by 7 millimeters of aluminum. And gamma rays will go through both the paper, the aluminum, and they're stopped with about 1 meter of concrete or lead. So much more stronger penetrating power because these particles have a lot more energy than the other ones. So next we're going to talk about artificial transmutation. So those previous examples were natural transmutation. This is transmutation that just happens on its own. You don't need to do anything. These particles are naturally radioactive due to their ratio of protons and neutrons in their nucleus. They just spit out this radiation all on their own naturally. Artificial transmutation is when the nuclei are bombarded by accelerated particles at incredible speeds, which cause the nuclei to become unstable when they collide, and it results in the formation of radioactive isotopes. We make an unstable arrangement of neutrons and protons in this very temporary mixture of elements when they smash them together at incredible speeds, and those radioactive isotopes decay, and they emit radiation and transmutate into other particles. So here's an example. Here is a helium atom or an alpha particle, and it is going to be combined with a isotope of nitrogen-14. So they have to give you one of the missing pieces or you can't do this. So if they gave you this much, you should be able to figure out the unknown product here. Okay, so one of these two products they'll always give you. And you just use the same concept that we learned earlier to find the missing pieces. The mass of the numbers, the sum of the mass numbers on the right needs to equal the sum of the mass numbers on the left, and the sum of the atomic numbers on the left need to equal the sum of the atomic numbers on the right. Okay, so let's do the mass numbers first. I have 4 plus 14, that's 18. On the product side, I have 1. So that means my missing mass number here must be 17. Again, that's not specific enough to identify the element. We need to do this from the atomic number. So let's do the atomic numbers. 2 plus 7 is 9. On the product side, we have 1. So my missing atomic number is 8, which means that I am dealing with the only element on the periodic table that has an atomic number of 8, which is oxygen. Okay, so here's another example. What nucleus is represented by the X? So go ahead and give this one a try. Okay, so as always, the sum of the mass numbers needs to be equal on the left and the right. So I have 27 plus 4 is 31. On the right, I have 1. So that means the mass number of my missing element is 30. On the left, I have 13 plus 2 for atomic numbers, that's 15. On the right, I have 0, so that's easy. My atomic number on this mystery element must be 15. And then you just scan your periodic table to see who has an atomic number of 15, and that is, of course, phosphorus. So we are artificially making phosphorus 30 by bombarding aluminum 27 with an alpha particle. Okay, so another thing you might be asked is to identify whether something is natural radioactivity or artificial radioactivity. So this is really easy as well. So in this example here, if I have carbon 14 and I'm not doing anything to it, so it's just decomposing all on its own into nitrogen 14 and a beta particle, that means it's natural. I'm not bombarding or smashing anything into this carbon 14. It's just by itself, it's breaking down into these products here. So this would be natural radioactivity. Same thing with the next choice here, rubidium-87. It's just spontaneously decaying according to this reaction into a beta particle in strontium-87. That's natural. Next, uranium-227 is transmutating or turning into thorium-223 and an alpha particle. Notice that it's only one reactant on the left, 2 products on the right. That makes this natural radioactivity. Next, we have a aluminum 27 plus a alpha particle or helium. So this is a bombardment here. So this is something slightly heavier being hit by something slightly smaller particle, and we're combining them to make something bigger or heavier here. Okay, and the other giveaway is I have a second product. So if I have two reactants and two products, that is artificial. Next, I have another natural. Carbon 11 is breaking down all on its own. We didn't hit it with anything, so that's natural radioactivity. And the next two are both artificial. Two reactants on the left, multiple products on the right. That's artificial radioactivity. So in summary here, we're going to use table N and O when answering questions about transmutations. You use table N to figure out the mode of decay, and O to look at what those particles look like. So when you write your nuclear equations, you'll have the right symbols. When you're figuring out the product of your nuclear equation, remember the sum of the atomic numbers of the reactants always equals the sum of the atomic numbers of the products. And the sum of the mass numbers of the reactants equal the sum of the mass numbers on the products. Only the atomic number of your unknown species should be used to determine its identity, because the mass numbers aren't specific. The mass numbers could be the same or different depending on what kind of isotope you are producing in your nuclear reaction. You want to get it right 100% of the time, and the only way to do that is to identify your element based off atomic numbers. Remember, natural radioactivity always has one reactant and two products, and artificial radioactivity always has two reactants and at least two products.